Good afternoon, good evening, everyone. And thank you for joining today's webinar on accelerating functional mockup models. This webinar will be led by Jacob Verwerka. He has years of experience building application and services for computer-aided engineering, simulation, and modeling workflows. At Julia Computing, he's working to bring the latest scientific machine learning techniques to industrial simulation and modeling. And during the webinar, in case you have any questions, you can type it in the chat, and we will answer all of them at the end of the webinar. Over to you, Jacob.
Thank you very much. So we at Julia Computing are excited to introduce JuliaSim for simulating reality. And the Julia programming language, as you may know, is rapidly growing. Its strong community is having significant impact in many scientific fields. And in order to further advance scientific methods and discovery, the language founders, along with a few strategic partners, started Julia Computing. And the foundation of Julia Computing is Julia Hub, which is an enterprise computing platform for distributed, cost-effective, and reproducible computing. It's really designed to be the ultimate Julia development experience. And it provides an ability to frictionlessly scale to industrial problems. And we're going to be looking at an example of how we achieve that very soon. But just to kind of give you the lay of the land, we have additional applications on top of this foundation, and these applications are for the variety of fields that we're working in. So today we're interested in physical simulation, so we're going to be looking at JuliaSim. But this just kind of, again, just gives you the lay of the land. JuliaSim is a powerful application that can do what it does largely in part of the advancements of Julia Hub. And so with that, I've kind of told you who we are now. You as engineers, you strive to create elegant designs. And in order to maximize efficiency, you incorporate modeling in the design process. And when you do that, you can experiment with multiple different designs, variable conditions. You can set up models, analyze your results, and iterate through this process with new experiments, right? Any decisions that you make along this process are driven by data, and ultimately, that data helps you arrive at better designs. And this is a picture of what industrial modeling can look like. It doesn't always work out that well, though, right? There's always challenges. And in this case, the challenge is time. So runtime of your model is something that can jeopardize all of these benefits. And it's rampant across any industry, right? This is not just geared at any particular industry, but accelerating this model is a difficult problem. You need experts who, oftentimes have to have knowledge of the domain, high performance computing, many technical aspects, and it's typically not a fast solution, right? And so that's the problem that we're looking at today, and then we're going to offer a solution. And all of this is to try to provide that freedom to the engineer so that you can have more time for that discovery process and ask those questions that just weren't feasible to ask with previous tooling that you used. And so with that setup now, let's just walk through an example that is something very analogous to maybe what you do today or what you could see in several industries. So let's say that you have a model that takes 2 hours to simulate. One run, not that bad, right? But as soon as you engage in a process, let's say you're optimizing control parameters where you have to run this 2-hour simulation many times over in a process, it's kind of trial and error. It's discovery in itself. That 2 hours can easily explode, right? So let's just say that you do this optimization run 1,000 times, because it's not that hard to imagine, because you might do 200 at a time, tweak some things, try again. So quickly in this example, that 2-hour model turns into 2,000 hours. At the end of it, you still have to perform a test run. And so now we're looking at 2002 hours, which is no small amount of time, right? And that equates to over 8 days, and that's if you're working on this nonstop, which is never the case. And so, 8 days of real work translates into probably several weeks, if not a month. And so this is the crux of the problem. And this is where we step in, and we want to offer a solution by adding one step before we begin this optimization, right? And so we take that 2-hour simulation and we create a surrogate model. And so this surrogate model is going to be generated by bursting compute on Julia Hub. So what we're going to do is we're going to take thousands of samples. So we're going to run this many times, but we can do that all in parallel. And so we can take those thousands of runs and really condense that down. We're going to call it 4 hours in this case. And what you're going to wind up with is a much faster model. And in this example, we're going from 2 hours down to a minute. And so right up front, you have that surrogate training process, which is going to take about 4 hours. And then you're going to have that same optimization step where you're going to try to tweak the control parameters and find optimal zones for each. But 1,000 runs of a 1 minute model is now 1 hour, 1 and 2/3 hour. So that is knocking that down from many weeks, right, to no time at all. And then you perform a final test run at the end to just make sure that everything looks good with your original model. And the end result is something that can be achieved in a workday. And that's really the story here. So we're talking about runtime, and a lot of times it's tempting to kind of dive into the technical aspects of runtime. And yes, a minute's a lot faster than 2 hours, but the real story here is what effect that has on the workflow, on your product development cycle. That is the larger story that I think can sometimes get lost when we talk about speed and computing. The engineer at the end of this is the one that we're trying to empower, that we're trying to give some power back to have the time to ask more questions and to create that space for innovation. And so we're already employing this in several fields. This is an example where we took an HVAC model. It's about 8,000 equations, and we saw a significant speed up of 570x. And just to kind of dissect that a little bit, we did see a speed up of about 6 times when we just implemented this in just native Julia language. And then the surrogate training process on top of that was an additional 100x. So all of that coming out to just under 600 times speed up. And again, this is all made possible by this blend of classical physical modeling with scientific machine learning techniques. So what you wind up with is this kind of semi-neural ODE, right? It's physical in all the senses that we kind of understand, but then we're cutting out a lot of the really time-intensive processes where we just don't see state change. So there's no point in calculating that every time, because we can use machine learning to gain some confidence that we know the answer there without having to actually perform all of the differential equations. So this is one example where we've seen a significant speed up, and that's the circle on the far left, but it's not the only one. So taking that same 8,000 equation system, but ramping it up to over 100,000 equations. And this is a scalable building model with equipment. For reference, this is something that with current tooling is about real time. So we were able to achieve an 80 times speed up, and 80 is a lot less than 570. But when you put that in the context of what's currently available with real time, so let's just say that you want to simulate a year. A year in simulation time is a year to compute, but we can knock that down to 4 days with an 80 times speed up. So something that, you know, an engineer might not have even thought about doing or trying, it's just not feasible, suddenly is, right? And that is really the power of this technique, and why we're really excited about it. And I've shown you two HVAC equations. This isn't limited to that. It's really any industry. So on the far right, we have a 1200 equation, nonlinear circuits model with a 274 times speed up. And so, you know, really any set of differential equations is fair game here. And I'm gonna actually show you how we can do this. I'm gonna walk through an example where here we're just looking at an example of a DCPM motor. So there is an armature connected to the motor, and it's going to start at rest. And then as we apply load, we're going to see voltage change. And then this whole model is just going to investigate the influence of that armature temperature change on the motor. Don't worry too much about you know, this particular model if it's not familiar to you. I do want you to take a look at the model parameters in the bottom right-hand corner, just because we're going to see these later, and this is going to help you understand how we might actually configure and generate a surrogate of your particular problem. So in this case, we have a model with the parameters VA, VE, T load, and J load. And so this is the problem that we're going to be looking at as we walk through our example. But it's also really important to note that what we're going to start with is an FMU. So odds are, if you're here, you kind of know what that is, but it's the functional mockup unit, which is anything that follows that functional mockup interface. It's that standard model API, so that you can take this model and collaborate with different teams, all different modeling tools. And so what we're offering is really, if you're doing modeling and you're using this standard, you can ingest this step. You can put JuliaSim at the beginning of this process to create this fast approximate, and then we're going to give you back an FMU that you're used to using anyway. So this can be put right back into your workflow with minimal disruption, right? That's really that's the goal here. And so with that, I think I am ready. I'm gonna just switch screens here real quick. So hopefully now you can see, it looks like you can. You can see the JuliaSim FMU Accelerator. Now, again, this is a Julia Hub app. And so this is an application running on Julia Hub that you launch just like any other application. When you do, you're actually going to configure the machine that you want to spin up for this particular application. I've already done that, and so once it's ready, you can hit connect, and it will connect you to your application. The important note here for the FMU Accelerator, remember, we're going to leverage compute burst in order to generate these accelerated surrogate models. So when you come in here and you select, a machine with 4 CPUs and 4 gigs of RAM, for example, that is what's going to be used for the GUI application. However, whenever you actually send this job off to compute a surrogate, it's going to auto scale depending on your configurations and the complexity of your model. So that's a detail. We can come back to that later. But yeah, just kind of take note of that. And so just taking an overview right here, this is our dashboard. So we can see the different models that we've run when we started them, the progress that they're in. It moves through several different states, and the states are going to be setting up the model, computing the surrogate. We're going to compute diagnostics, and then after that, we're going to compute the generated FMU, the accelerated FMU. And so I'm going to walk you through how you actually configure this and start a job, and then that's going to run. But I'm going to take you to an example of the diagnostics for this same job, so that we can see, we can try to analyze and understand the model that we get back from this whole process. And so to begin, we're just going to click new job. We are going to upload our FMU. So just that binary FMU. And so that's happened. And so we're going to use that standard model API to fully understand and describe all the model parameters and the hierarchy of this system. And then here is where we can configure this surrogate. So you can just kind of see here what options we have. So we have the algorithm. This is the algorithm that we're going to use to compute the surrogate. And then reservoir size is the number of nodes. Remember, this is a semi-neural ODE. So this is the number of nodes that we're going to use to compute the surrogate. The number of sample points is the number of simulations that we want to run. And your selection for these really depends on the problem that you're working with, right? So what I'm going to show you in this example, it's a simple example. You're not going to see, I believe we use 3 and 3. I'll show you that in a second. But how many nodes you select, how many sample points you select, this is dependent on the complexity and the structure of your problem in particular. And so we can provide some rules of thumb, but this is something that is going to be really specialized depending on what you're trying to do. And then down here, we can select the time span that you are wanting this model to run for. So you can set the start, end, and time step values here. And then for parameter space, this is where we can define the bounds of our parameters. So when we loaded that model, we had everything. So I'm going to go ahead and load. So this is a configuration that I had ready just so we can kind of see what we're going to run this with. So we're going to choose the nonlinear projection algorithm. We're going to have a reservoir size of 3 and 3 sample points. This is going to run from 0 to 3 with a time step of 0.1. And then for each of these different parameter names, we define the parameter space and a sample value. And so when all of this is configured, no, I loaded that. You can also export this config to use it again later for archiving, whatever you might be wanting to save that for. But when you're ready, you can hit start new job. And now this is, as I said, this is submitting a job to Julia Hub. It's auto scaling depending on how we configured that and the size of this job that we're wanting to compute. And then as this goes, we'll see this move through different states of computing surrogates. One thing that happens shortly after is generating the diagnostics. And that's another thing I want to show you because it's a very important point of what we're doing here, right? So you're taking a classical physical model that in theory, you understand exactly how it works. What forces have particular relationship or influence on others. This approximate model that you get back is going to cut away some of that, and you're not going to necessarily know everything, but you still need to know the fidelity of it, the accuracy, where does it perform well, and so how do we do that? Well, when this is ready, you see here report. We can click on this eyeball, and it can take us to our diagnostic report. And the first thing that we see up here right at the top is it tells us the speed up that's achieved with this model. And so automatically, this example is 200 times faster than what we had before. And this is a small example. So one thing that is important to note as well is kind of the bigger the example is, the more opportunity there is to cut away some of this complexity. And so we do expect that for large enough systems, we expect this to even improve over what we're seeing here, but that's just something to note. And then as we look at this diagram, we can see here that we have each vertical axis is a model parameter that we were dealing with. So here's a model parameter, and then at the top and bottom of this axis is the parameter space that we used to train the surrogate. So what connects everything in between is each result of every permutation of these parameters, right? And then over on the far right end is our error. And so we can see here with this histogram, we have the number of results that fall within this certain error that we're seeing on the axis, where dark purple corresponds to 0 or no error. And then up here at the top where we have 1, we can see it's bright yellow. So this is an example of where this model is not performing as well as the rest of these points, right? And again, we want to provide mechanism in order for to help people investigate these models they get back. So we can do that by carefully choosing how we display this information and then allowing you to interact with this. So if I just click and drag across an axis, then it's going to filter out some of this noise. So I've chosen this JLoad parameter from space 0.42 to 0.16, excuse me, 142 to 1.6. And anything outside of this is not selected, right? And this is these changes, these selections are propagating throughout this histogram. They're also going to change these two diagrams we see down here, which on the left in the yellow is the percent error, and on the right is the actual values of the two different models. In yellow is ground truth, and in purple is the surrogate model. And so you can see as I slide this, as I change some of these options, we can actually see how that would impact the other graphs. And so let me just kind of walk through this with an example. So let's say that you are you're wanting to maybe even improve this model. So maybe you want to take a look at where this model is underperforming, and you want to retrain across those parameters, see if you can improve the overall fidelity of this model. So to do that, we're going to cue into these yellow lines, because the yellow lines associate with the higher error. So then we're just going to try to identify where they cluster, and that's going to give us our interval that we should think about retraining. So looks like there's a couple yellow lines down here at the bottom, and it looks like I've successfully selected that. Let me just take another look here. So yeah, we've got a couple down here. And then if we just say up here, here's 2 points as well. So over this small parameter space is where it's kind of hit or miss, right? So maybe we need to retrain across this space to try and make sure that these points all fall in a lower error. Or conversely, we could ask the other question, like, where can I use this model and really have no concern over the fidelity? And so instead of queuing in on the yellow, let's try to look at this, the dark purple regions. So that looks pretty good. There's one up there at 7, which I think, yeah. So you can kind of see how. So now it's successfully filtered out anything really above 5, and I can now feel pretty confident that if I were to use this model over this select parameter space, I can have really no concerns about the results I get back, right? And you can extend this to any different number of parameters throughout the model here. And then also, let's just say that you don't like how these are laid out and doesn't really fit with your mental model. You can move these around. All of this is really designed to be flexible and to answer the questions that any particular model modeler may have with the results they get output from this process. And this is kind of giving you the 30,000 foot view, and then when you want to zoom in a little bit further, you can look at these lower charts where if you see this slider for parameters, all the way on the left-hand side is the lowest error, and all the way on the right-hand side is the highest error. So let's just look at worst case scenario. If I slide that, so this is telling me that there's pretty high error occurring between time 0 and 0.5. So that's going to be this portion of the right-hand graph. And then I can zoom in further to just kind of get a better look. But because of the interactivity, you can also just kind of hover and see the values and use all of this to ask, that question that you might have over how you're hoping to use this model and where it's going to be important. You can do this over all the different states of your simulation. And so that's really the goal here, is just to provide you with the tools to investigate where you can use this model and feel confident about the results. And so that's really it for the diagnostics. And with that, I'm just gonna switch back to the presentation really quickly. So remember that when this is all done, what you're gonna wind up with is another FMU that you can use just like your original model, so it fits right in with your workflow. And so all of this is made possible in leveraging the Julia Hub, the ecosystem from Julia Computing. And so what we're able to do is accelerate these with really fast scale up, right? We're throwing compute burst at these problems up front and then reaping that reward many times over as we use the model. So anytime that you have a model that is a bottleneck in your design process, it's really large, it's the one you don't maybe look forward to running, or it's going to take a long time, that's a good candidate for something you might consider this approach for, because that initial upfront investment you can reuse over and over, right? And these components are again meant to be composable. We want to allow reusability everywhere that we can, and the Julia Hub platform is also what's allowing us to use these latest scientific machine learning techniques and really leverage the advancements of modern algorithms, modern techniques. And so one other detail that the astute among you will know that I just kind of glossed over is you do have that compute bill. So when we generated that surrogate and we spun up a bunch of simulations in parallel, you do have a compute bill, and that's going to be the going price that you can see from Google GCP.com. But the question, what it really is an opportunity to ask a different question. So yes, it takes an investment to compute that surrogate, but now you're faced with a different kind of question of, is it worth X dollars to finish this problem today or to have an answer tomorrow? So, instead of it taking many more weeks, maybe months, depending on your problem, to get to that solution, depending on the scenario that you find yourself in, the particular circumstances, maybe it would just do wonders for your design cycle for you to be able to hit the fast forward button and solve that problem today. And that is the flexibility that this solution is offering. It's really, it's case by case, and it's definitely a strategic use. So like I said, you want to target the model that you're going to reuse that really takes a long time, but it is going to allow you to look at your development cycle differently. And so that's the real takeaway here. And with that, I will open it up with questions. All of this is again it's all in an effort to provide a little freedom to just make that space for innovation. And so with that, I'd like to hear from you guys. Know if you have questions about this, if you'd like to see something else, I'd love to hear it.
Yeah, there's a question from Christian in the chat. I think Sharon answered that.
So do we support ME and or CS, that question? Sorry, I'm catching up here.
Most of the questions were answered by Sharon and Anas. I think if you scroll down, and there's a question by Christian. He asks, which size does created FMU have? Does it run Julia code inside, or can you do code generation? Scroll down and you'll see the question.
Yeah. Yeah, so I believe Sharon just addressed that. So yeah, it's it depends. The size depends on the complexity of the input FMU and the target platform, because we support both Windows and Linux, depending on what you might be, what your current engineering modeling workflow may run on. And then the other question, I believe, is something about code generation. I'm sorry, I'm reading on the fly, but yeah, it runs with Julia code. Is it 110 or 100 megs? Again, I think that would really, yeah, it would depend. It's definitely not one. But yeah, it would depend on your problem, and I think on the order of 100 is probably a safe bet for most problems. So if we have a commercial CAE software or open source FEM's code, how do we generate a surrogate code from these resources locally or in Julia Hub? So JuliaSim is an application that runs on Julia Hub. So what we would likely do there is you would have a subscription for the JuliaSim product, and then you would go through a similar process as what you saw me do. You would upload an FMU in the case where you have a commercial CAE software. Many or all of those tools, really, I believe it's in the order of hundreds, all support that FMI standard. And so if you can generate a model following that standard, then you can upload that directly as you saw me do. And the reason that's going to run on Julia Hub is because that's where we have the ability to perform that computational burst, right? So so it's going to run on Julia Hub. It's going to leverage the auto scaling that we have configured, and what you're going to get back is another FMU that you can ingest in the workflow. And can you optimize parameters for a vehicle model? Yes, and that's something that I won't speak to now. We do have many other offerings that are all part of the JuliaSim platform, and I think that's a good kind of segue. So what I shared with you is the JuliaSim FMU Accelerator. That is one application of the JuliaSim platform. JuliaSim is really a full simulation modeling platform. So it's a place where you can build, run, analyze, iterate on that process on your modeling development process. So, excuse me. So if you, at the moment, if you are developing in Julia, developing your models in Julia, then JuliaSim provides you with the best experience in order to perform that development. If your models are not using Julia at the moment, and you actually build the models with graphical tools or with other codes, that's where this FMU Accelerator is a good fit for you, because you don't necessarily have to port everything that you're doing at the moment. So So that's where JuliaSim is kind of offering different levels of access depending on where you are with maybe adopting Julia, with maybe you're just happy with your workflow, maybe you're locked into some of the tools that you currently use. But really, no matter which of those is you, we're working to make sure that you can benefit from these advancements from JuliaSim. And one challenge with machine learning is to choose the ML model that you want to train. Is this solely up to the user, or are there suggested models created from analyzing the input FMU in Julia Hub? So we're going to offer different algorithms, and that's going to continuously evolve. A lot of what you see, so everything that you've seen here today is using continuous time echo state network algorithms, which we have published papers about. If you'd like to learn more, definitely check that out. And the goal there is to provide many different offerings so that we have a good fit for whatever problem user may come with, right? And then there's a few different trains of thought. You know, for the user who maybe doesn't want to dig in and be responsible for deciding which algorithm is best suited for their problem. You know, maybe we can provide some suggestions or you know, auto select, but then obviously you're on the flip side of that, you're going to have users who want to try a particular training method for their problem. And so that's always a balancing act. And without, you know, committing one way or another, I can tell you that the JuliaSim team is working to make sure that the algorithms that we have available, that we provide, are encompassing, you know, performing well for as many different kinds of problems as we can wrangle. So what you've seen today is CT-ESN. I encourage you to go read more about that if you're interested. If you have any more questions, then say reach out to us, and we can see if your particular use case is better fit for what we have now or what's coming in the future. And I saw something about Dymola here. So just as another note, just to you know, be crystal clear, with the FMI standard, Dymola, Simulink, all these big modeling tools that are you know, ubiquitous in modeling space, all of these will have an option to export and use FMUs, so they'll follow that FMI standard. And so that's exactly what JuliaSim is aiming to do, is complement these workflows. So definitely don't, you know, it's something that you can use really no matter what tool you're on, as long as it follows that FMI standard.
Yeah, do type in your questions if you have any. Alternatively, you can also just unmute yourself and, you know, ask a question.
Yeah. Here is Christian speaking. Hello. So perhaps could you show how to deal with inputs? You showed how you deal with parameters, but how can you specify, let's say, also inputs depend, for example, there might be a frequency, a typical frequency or so for that you have to specify for inputs.
So where we're dealing with really just a data set essentially. So instead of maybe instead of a set of differential equations or differential algebraic equations, we're dealing with training over data. Is that the question?
So imagine you don't train the overall model, but a submodel that you would like later to include in a larger simulation model where you have typical inputs and outputs, but for the training you need especially the inputs. And these inputs, it's not sufficient to provide them with constant inputs, but you might somehow need to specify what typical inputs are. For example, which frequency content do they have, and it would be interesting how you could specify this.
So that's something I might defer to Anas, or yeah, I'm curious, Anas, if you have any thoughts on that.
Yeah, definitely. So what's supported right now is we take common input functions, which are parameterized. And then, so as a typical example, just to kind of give a mental model, take for example, like sine, and you can parameterize its amplitude, its frequency and such. And so what we do is we allow the user to select from these functions, provide a lower bound and upper bound, and then we include that in the training process.
Thank you.
Thank you for your question.
Yeah, we'll be around for maybe just a few more minutes, Jacob. Let's see if there are more questions coming in.
Sounds good.
I see there are no more questions coming in. Perhaps we can call it a day. So thank you everyone for joining today's webinar. Thank you, Jacob, for this wonderful webinar, and also Anas and Sharon for answering all the queries as well. In case any of you want to know more about JuliaSim, you can write to us at sales@juliacomputing.com, and one of us will definitely answer your queries or reach out to you. I'll just put the ID there. Yeah, there you go. So yeah, thank you everyone, and have a great day.